Now that you have acquired the shear force and the bending moment diagram, the next step it will be designing the reinforcement for the beam. Read the questions. The questions ask you to design the reinforcement at the midspan of beam B1 to 2. Referring to the key plan, beam B1 to 2 is referring to this stretch. The beam size is 200 times 450. The span is 5.6 meters. Based on the bending moment diagram, you are looking at the first stretch. There are two moments here. 127.8 is at the midspan, and 110 kN is at the support. Again, in the final exam, you will have to read the questions carefully to see which part of the beam you are asked to design. Sometimes you may be asked to design for the moment at the support. Sometimes you may be asked to design the moment at the midspan. If you are asked to design the moment at the midspan, the tension steel bar it will be at the bottom of the beam, while the top bar will be the compressions, as implied by the bending moment diagram. However, if you are dealing with the support here, you have negative moment. Now your tension steel bar will be at the top of the beam, whereas the compression steel bar it will be your bottom bar. You will need to be careful on this. Coming back to this question, you are asked to design the reinforcement at the midspan of beam B1 to 2. That means this will be the moment that you are designing, which is going to be the bottom steel bar. Therefore, your MED it will be equals to 127.8 kN. Next, you will need to calculate the effective depth. Before that, find some details and specifications of the beam from the question. The intended tension bar is H20, and the intended shear length it will be R8. You can sketch the cross sections of the beam for you to determine the effective depth. Taking this as an example, now your beam width is 200 and the height it will be 450. Your effective depth it will be calculated from the top surface of the beam until the centroid of your tension steel bar. To determine the effective depth, you will need the beam height minus the concrete cover minus the size of the shear length and minus half of the tension steel bar provided. The questions give you the concrete cover equals to 30. Your shear length is 8 and the tension bar is 20. Therefore, your effective depth it will be equals to the height of the beam, which is 450, minus concrete cover 30, minus the shear length 8, and minus half of the tension bar, which is 20 divided by 2. That gives you the effective depth equals to 402. In this case, the nominal cover is given. In the case that the questions do not give you the nominal cover, you will need to find the nominal cover yourself using Eurocode 2 in clause 4.4.1.1. This will be the equations for the nominal cover, which is equals to the C mean plus the deviations. The recommended value for the deviations it will be 10 mm. That means this is equals to 10, and the C mean it will be obtained from this equation, which can be due to the bar size, environmental conditions, and the minimum of 10 Eng-aim. The C-min bar can be obtained from table 4.2 in Eurocode 2. It depends how your bars are being arranged. If the bars are separated, the C-min bar can be obtained as the diameter of the bar. This is conditional to the maximum aggregate size is not greater than 32 mm. In the case that the maximum aggregate size is more than 32 mm, the C-min bar should be increased by another 5 mm. Normal concrete will have the maximum aggregate size 20 mm. Therefore, you may use C-min bar equals to the bar diameter. As for the C-min due to the environmental conditions, first you will need to know the classifications of the concrete. For normal constructions, normally we look at XC2 and XC3. XC2 is normally used for foundations, whereas XC3 are used for the other type of structural element. And then later you will need to check table 4.3n to see if there is any changes in terms of the structural class. Next you will refer to table 4.4n. You will start with structural class 4 and XC2, SC3. See if there are conditions that brings to you shifting or reducing the structural class. From there, you will be able to determine the C-min due to the environment. Substitute the value into the equations. You choose the largest value of the three. Bring it back to the equations for you to get the nominal cover. This is as the revisions for you. If you have difficulty understanding the process that was mentioned just now, you might need to refer back to our previous videos on how to calculate the nominal cover. Now coming back to the questions. Since the nominal cover is already given, you don't have to find the nominal cover. And then we proceed from the effective depth that we have obtained, 402 mm. Once you have obtained the effective depth, your next step now it will be designing the reinforcement. At the moment, we are not sure whether the beam is singly reinforced or doubly reinforced. You may refer to the floor diagram here. You will need to use the K to check whether the beam is singly reinforced or doubly reinforced. This is the equations for the K. The moment here, it will be the MED. FCK is given in the questions, which is 30 Newton per mm square. B is the width of the beam, which is 200 for the beam stretch B1 to 2. And then the D here, it will be 402 mm. The K now is found to be less than 0.167. When the K is less than 0.167, you know that it is singly reinforced. Singly reinforced member is relatively easy. All you need to do is to find the lever arm and then substitute into the equations to determine the reinforcement. This is the equations for the lever arm. Use the K that you have obtained, substitute into the equations. You get your lever arm. The lever arm now is 0.866D, which is less than 0.95D. Therefore, you will use the lever arm equals to 0.866D. Substitute the D into the equations, you get 348 mm. And then next, substitute the Z into the equation. Your moment here is the MED 127.8. FYK is given in the question, which is 500 Newton per mm square. Substitute the value, you get the AS required at 144. Refers to the table for the steel bars. The required steel bar area is at 144. Find the value larger than 144. Since the question specifies you are going to use the H20, you will require 3 numbers of steel bar H20 to have the bar area greater than 144. Therefore, you use 3 bar of 20 mm diameter, which is equals to 942, greater than 144. That means the amount of reinforcement bar provided is sufficient. In the case that the table of reinforcement bar is not given in the final exam, don't panic. You can still generate the numbers. Use the basic equations of a circular area, pi r squared. Since it is already specified, you need to use H20. Get the area of 1 bar 20 and then see how many rebars for you to have the area greater than the required AS. Then provide the AS, which is more than the required. As far as this example is concerned, the beam is singly reinforced. It is also possible that the calculation ended up with doubly reinforced beam. This normally happens when you have relatively large bending moment that is to be taken by relatively small beam size, which will give you the K greater than 0.167, and then you will use this set of equations for you to solve the question. Let's say now you need to design a doubly reinforced member. Knowing now your K is already greater than 0.167. For a typical doubly reinforced member, your lever arm will be equals to 0.82D, and the tension reinforcement bar, it will be at the limit. You require strengthening of the compression steel bar. In order for you to determine the AS, you will need to first find the AS prime, which is the compression steel bar. Use the K found by the equation here, minus 0.167. Those will be the additional moment that needs to be provided by the compression steel bar. Substitute into the equation. The D will still be the effective depth, whereas the D prime is referring to the effective depth of the compression steel bar, which is this. To determine D prime, you need the concrete cover plus the shear length plus half of the bar size, and then substitute the value, you get your AS. Next, you will need to check whether your compression steel bar has yielded or not. Check the ratio of D prime per X, whether it is more than 0.38 or less than 0.38. If you found that the compression steel bar has yielded, the stresses in the compression steel bar will be taken as the specified yield strength, which is 0.87 FYK. This 0.87 is due to the factor of safety of the material. For steel, the factor of safety, it will be 1.15. The 0.87 is due to 1 per the factor of safety of the steel. In the case that the compression steel bar has not yielded, that means you cannot use the specified yield strength of the compression bar. You will need to do the interpolations based on the strength diagram to determine the actual compressive stress in the compression bar, and then substitute it into the equation here for you to determine the AS. What you see here, designing a singly reinforced beam is much more simpler than doubly reinforced member, and there is no restriction that the doubly reinforced beam will not appear in the final exam. Coming back to this question, based on the calculations, the K is less than 0.167. Therefore, you will only need to do the singly reinforced beam, and you will need 3H20 as the tension reinforcement bar, with the AS provided greater than AS required.